tuning fork. I'll whack it against my hand. The times go back and forth, 288 times a second. They compress, they rarefy. When they compress the air, Jessica, what do they do to it?
It's condensed.
It's condensed. We have a high density location, right? And then it rarefies the air. What does it do then to the air? Yeah.
Wait, it rarefies the air outside?
It compresses and rarefies the air. Compress, rarefy, compress, rarefy, compress, rarefy, compress, rarefy. That's what it's doing. See?
Is that when the air decompresses?
Right, what's that called? If compression was high density, we have
Low density.
low density. So what you have here is high density and low density going back and forth as the air goes out. Now, you're going to look at this, and when I draw things on the board, it's going to look like a circle, but realize that all of the sound always goes out in 3 dimensions, which makes it class A sphere. So it's going to look like a circle when I draw it on the board, be various pictures, but remember it's a 3-dimensional thing, it's actually a sphere. Now, this particular tuning fork is missing something that most musical instruments have, which is some way of amplifying it. It's missing a sounding board or some sort of sounding cavity. So I could take this, I could put it against your desk. I could take it, I could put it against this. I could put it against, of course, the speaker. I could put it against all sorts of different things. My favorite is I can take it and I can put it against your skull. And what happens here is it actually vibrates your entire skull, yes? You hear it? I'll push harder here. Yes?
Yeah.
There we go. All right. Now that is my favorite part because it actually vibrates your entire skull and you can hear it very well, yes? Yes, good. Now, what's interesting as well is you can also take it and put it right behind your ear, and right at this particular location you can put it on that bone and you can hear it very well, yes? Yes. And what you're doing there is you're vibrating the inner ear. And they can actually use this to test your hearing. If you're having some sort of hearing issue, they can check to see if it's an inner or outer ear issue by putting it on your head at that particular location. And don't you worry, when we do the lab, you will get one of these.
Ooh.
You will get an opportunity to use the tuning fork. I know some of you are looking at it, you're excited, you want to be able to do. It is fun. You will get an opportunity next time to use the tuning fork. Okay, oh wait. So we have compressed air, rarefied air, high density, low density. This means that sound is what type of a wave? Danner.
Mechanical?
It is a mechanical wave, but I'm looking for a specific type of mechanical wave. Chen.
A longitudinal?
It is a longitudinal as opposed to a transverse wave. So what we need to look at now is we're going to look at a figure of the various the tuning fork and all of its various characteristics. So, as it fades in, you're going to see, this is exciting, we're going to have a picture. We recently, at my house, and this seemed apropos because we're talking about sound, we recently invested in a disco ball.
Ooh.
And this is a picture from our basement with the disco ball. Add a disco ball to any dance party, and it's much better. There we are, dancing to the disco ball. So, we have our picture of the tuning fork on the left. You can see it is compressing the air, rarefying, compressing, rarefying, compressing, rarefying, compressing the air, which means along the x-axis you're going to have position, and along the y-axis you're going to have density, making this a longitudinal wave. All right. So now, what is the human audible range? Human audible range, what it is considered that all humans can hear.
Approximately 20 to 20,000 hertz.
Approximately 20 to 20,000 hertz. So the human audible range is approximately 20 to 20,000 hertz, or up to 20 kilohertz. Now, you should be aware that we don't hear frequency necessarily. We interpret frequency as pitch. It's our human audible interpretation of frequency. Which means we're now going to look at, or hear this, I guess. This is a frequency generator, a variable frequency generator, and it creates a sine wave, and I can adjust the frequency clearly. I don't know how old this is, but the one thing I can tell you is that the last time it was serviced was November of 1966. Which is great. I hope it never breaks, but it's a wonderful thing. Okay, here we go. So right now, this step function is at 1. Here we have 20. That means that this is at 20 hertz. Right now, these speakers are vibrating back and forth 20 times a second. That's literally what it means at 20 hertz. And this is the very low end of where you can hear some sort of pitch. We're going to increase. We're now at 30 hertz, 40, 50, 60. We'll talk about that in a minute. 100 hertz, 200 hertz. This is the top of where I can get to here. So I need to go back down, and I'm now going to multiply each of these by 10. So we're now at 200 hertz, 300 hertz, 400, 500, 700, 1,000 hertz, 2,000 hertz. Still at 2,000 hertz, 3,000 hertz, 4,000 hertz, 5,000, 6,000 hertz, 7, 8, 9, 10,000 hertz, 11,000 hertz, 12,000 hertz, 13, 14,000 hertz. We're going to take a pause for a moment. 14,000 hertz. Now we're getting to the high end of the human audible range. So what I want you to do is I want you to raise your hand, illustrating that you can hear this. When you can no longer hear it, please lower your hand. 15,000 hertz. 16,000 hertz. I'll turn it up. 17,000 hertz. 18,000 hertz. I'll turn it up just in case. 19,000 hertz, right around there. So you can see that the human audible range, this is an approximation. Not everyone has the same human audible range. We can't all hear up to the same frequency. And eventually, we'll take a few moments and talk about what I like to call voluntary early onset presbycusis.
Wow, that's a big word.
Not yet. We'll get there. All right. Oh, by the way, these are the speakers that I purchased in 1991 when I was in my freshman year in college, and I had to replace them, and we'll get to why a little bit later. All right, we've done all those. Okay, now, one thing we need is the speed of sound in air. Now, the speed of sound in air oh, and just as an aside, I'm going to try to stay above this. Actually, you know what I'm going to do? Above that line, because I'm aware that the speakers are making it a little bit difficult to see below that line for some of you. Okay, so the speed of sound in air is temperature dependent. It's equal to 331 plus 0.6 times the temperature in degrees Celsius. Now, this equation for some reason is not in your book. I don't know why, but the speed of sound in air is very important, and it is dependent on the temperature of the air. And this equation has to do with the temperature in degrees Celsius. So remind me, what is temperature, Christina? Temperature.
Measure of energy.
What kind of energy? Yes, it's a measure of energy. Specifically, what kind of energy?
Average
Kinetic energy, average kinetic energy. Kinetic energy, remember, 1/2 mv squared. Temperature is actually a measure of how quickly the air molecules are moving. We're measuring the temperature of air, which means the higher the temperature, the faster those molecules are moving, and the faster that the sound will actually propagate through the air. That's one of the reasons that sound is, the speed of sound is dependent on the temperature of the air. Now, I talked about the sound wave coming out from here. And I said it is a sphere. And I said when I put it on the board, it's going to look like a circle, which is what you see on the board. This is essentially an artist's rendering of ripples on a pond, but it's a good representation of the way the sound is moving out from the middle. You can consider the sound source to be right in the middle and the sound to be moving outward. But again, it's moving outward in 3 dimensions, and that's very hard to illustrate on the board. So here we have a visual representation of the sound. Now, I also like this one. We'll come back to this one in just a minute, because this one right here is actually moving. So what you see here is the sound source itself is stationary, but what you're seeing is the time component here. So what we're saying is this is a sound source, and right at this moment the sound begins, and then you can see the sound is moving outward from the middle. We're going to talk about specifically what is going on here, what we're representing. So in this picture, you can see we have our sound source. Sound source is right in the middle. So this is a stationary sound source. And the sound is going out from the middle. Now, each one of these circles is a wavefront. Now, a wavefront represents a crest of the wave. So remind me, what does that mean, a crest of this sound wave? What does that mean? Right, I agree that's like visually what it looks like as far as the sine curve is concerned, but I want to know specifically what it means for a sound wave. Heather?
Highest pressure.
I'm going to talk about density. So the highest, location of highest density, right? That's what that wavefront is. That's where we have a crest. Okay, then the sound is moving outward from the middle. Again, we remember that that's actually in 3 dimensions. So it's actually moving out in a circle or in a sphere. And these are rays that just represent the direction that the wavefronts are traveling, that the sound is moving here. Now, if this is a wavefront, what then is this, the distance between 2 wavefronts or 2 different crests? Kraus?
The wavelength.
That is the wavelength. If we were talking about the time it took, bless you, for the wave to travel that distance, that would be the period, but in this particular case it's the distance, so that is the wavelength. So that's for a stationary sound source.